did his graduate work at Santa Cruz with, I guess, Mosley. And then after that, he went on to do postdocs at Caltech, and then followed that up with a postdoc at the Institute for Advanced Studies, and then he's moved on to a faculty position at New York University, where he's been for several years now. And he's best known for his work on GRBs and high energy astrophysics in general, and he's a particular expert on numerical methods such as hydrodynamics and MHD, and he's going to tell us about some of that stuff today.
Okay, thanks a lot, Shane. Is this on the? Okay,
it's just recorded.
It's just recording. Okay, good. So thanks for inviting me to CITA. I was here about 10 years ago, so we get a lot of fresh faces. It's nice to be back. I'm going to talk about several things, but kind of the most exciting, I think, is some very, very recent progress in understanding what happens when a gamma ray burst goes off in space. And, you know, the model are based, at least for the long bursts, on the collapse and explosion of a rapidly rotating massive star. This is probably a Wolf-Rayet star, that's why it's blue. And the idea is that a relativistic jet of some form can propagate through the star, escape the surface, and then collide with itself, dissipate some way, and collide with interstellar medium and produce afterglow radiation. This turns out to be a very interesting problem, how a beamed relativistic shock wave decelerates and spreads laterally. So this beam, this is actually outflow from the star, but it's going to sweep up the ISM and drive a shock wave. And that shock wave is going to radiate brightly, and that's for months. And that's what's detected as the afterglow radiation at a broad range of wavelengths, everything from X-ray starting out early all the way down to radio at late times. But so this is a very beautiful problem in numerical relativistic hydrodynamics. And I've been working on this problem, as Harold knows, for about 10 years now. It's not a trivial problem, it's quite challenging, but I think it's finally being solved. And I'll show you why. So just to give you a brief outline, this is a diverse crowd, so I'll give you a little bit of an overview of GRBs. So most of you probably know this already. I'll discuss a little bit to motivate the afterglow dynamics, what the central engine is like, but then I'll focus on this. This is the recent work, afterglow dynamics and light curves. So we can calculate the radiation for observers with arbitrary angle with respect to this jet that's coming out of the star. And then in order for this light to be produced, it must be, there must be magnetic field in the outflow. And the ISM is not sufficiently magnetized for the synchrotron radiation to be produced unless a magnetic field is amplified somehow. And so I'll talk in general about relativistic MHD turbulence, but how that can amplify magnetic fields. So very weak magnetic fields can be amplified by a turbulent dynamo. This is relevant for the afterglow light curves, but it's relevant in general. It's also very important for merging neutron stars, where the stars touch and merge, and there's a shear layer that generates Kelvin-Helmholtz instability that drives turbulence in a relativistic MHD fluid, which I'll show can generate extremely strong magnetic fields before the remnant presumably collapses to a black hole. So I'll show some of that, and then I'll summarize. And if I have time, for those of you who were here this morning at the fluids group, I've also recently been working with a student on protoplanets. And they seem very different, but the numerical techniques which have been developed recently in my group, I think apply to both equally well, and it's a very interesting topic, so I'll show you some of that if I can. Just a brief intro to the background of GRBs. I think most people know that these are bright flashes of non-thermal, soft gamma rays. And then from BATSI, for example, there's thousands of these things. And typically they're flashes that last for a second or so. The interesting thing is they're on and then they're off for a long time, they're quiescent, and then they turn back on. And some of them fluctuate, turn on and off completely on timescales of milliseconds. And that, it turns out, since the spectra of the bursts are non-thermal, compactness arguments require that the Lorentz factor of the outflow be 100 or more. And that's just because you need the source to be big enough so it's optically thin. If it's going to fluctuate on a millisecond timescale and not have that variability be washed out by light travel time effects across the blast wave, it has to be moving relativistically, so you're only seeing the patch of the fluid that's moving towards you. So if you have Lorentz factors of 100 or more, then you can match this thing, rapid variability plus non-thermal spectra. But the really interesting thing is, we know the total energy of these explosions, And since we can infer the Lorentz factor, we know that it has to be a very tiny amount of mass involved in the explosion. So how does the star do that? A 20 solar mass star somehow is able to produce a relatively clean outflow that has very few baryons in it. Possibly it's an electromagnetic outflow which would have none. And the observational story that from the late 90s, which really made this field of great interest, was the Compton Gamma Ray Observatory would see a burst, but then that's only located to a few degrees on the sky. But then this famous burst, 990123, and then earlier ones as well, the Beposac satellite was able to point quickly at the location of the GRB, and it had an X-ray telescope with much better angular resolution, so 1 arc minute. So it saw a fading source. So here it is, the afterglow of gamma ray burst seen in the X-rays. It's here, and then a day or so later, it's fading. And then you know the position to an arc minute. You can search really carefully in the Palomar Sky Survey, and here it is. So there's this optical transient. Now we really know where it is accurately, and you can go back and look with HST later, and lo and behold, the gamma ray burst was in a star-forming region of a low-mass galaxy in the early universe. These are things that are forming galaxies in early structure formation at redshifts of 1 or 2. So this particular one was at a redshift of 1.6. And then we can infer its total energy, which is huge. So more than the rest mass of, let's say, a neutron star or the sun. So that immediately makes you think that, well, you can throw a few stellar masses into a black hole and produce this much energy. But they're beamed. So this is the isotropic equivalent energy. The real energies are more like 10 to the 52 ergs when you correct for beaming. And I'll discuss how we infer the beaming from carefully measuring the afterglow radiation. This thing you could almost have seen with your naked eye, and it was halfway across the universe, and this is just the afterglow radiation. There's actually much more energy. So we think that these things are impressive. And there's a whole range of redshifts. So a lot of them are redshifts of a few, but now they're really probing the early universe. They're also very important for understanding the very early universe when the first stars formed. And so we have, there's a competition with AGN and early galaxies, but there were gamma ray bursts at redshifts of 8 or 9. There's probably ones already in the data that are a higher redshift. We just don't have a detected redshift for them. Okay, so what's causing these things? Very generically, we think it's the accretion of a torus rapidly onto a newly formed black hole. That's a very popular model, a hyper-accreting black hole, and that can be formed in a variety of ways. The very popular model for a long time, and still a candidate for the short bursts, is the merger of 2 neutron stars that are in a binary system, or a neutron star with a black hole binary companion, and a black hole forms, and there's a small torus. There are other channels as well, a low-mass X-ray binary, which could be a normal star dumping mass onto a neutron star, which collapses to a black hole. Would do the same thing as would a black hole white dwarf merger and other things. And then the one that I worked on for my thesis was the idea that a massive star collapses, and since the star is rotating and forms a black hole at its center, that the gas as it tries to fall into the black hole that it's formed at its center actually falls into an accretion disk, which heats the hole rapidly. And the key thing is that the star is small enough in radius, so about the size of the sun, so that a relativistic jet formed near this black hole can get out of the star in a time scale that's short compared to the duration of a long GRB. And it turns out that is the case. It also turns out when you do look at the supernovae that have now been detected associated with gamma ray bursts, they are in fact this type of star. The type 1bc supernova comes from a Wolf-Rayet star, which is a massive star, the core of a massive star that has a small radius. Of course, we don't see this, except when we see the supernova, we don't see the source of the GRB initially. We only see it from this region far away from the engine where there's dissipation in the relativistic flow. What we could observe it, presumably, neutrinos or gravitational waves if we had sensitive enough detectors. So the idea is that this is a very strong model at this point for the long gamma ray bursts, and these are possible models for short gamma ray bursts. I should have said that there are 2 classes of gamma ray bursts. The long ones have durations of 30 seconds or so, and the short bursts have durations of 2 seconds or less, or something like that. So there are 2 distinct classes. What do we think happens when a massive star collapses? The basic idea is that over stellar evolution timescales, the core of the star gradually evolves into denser elements and or heavier elements, and at some point you're left with an iron core of a few hundred kilometers, which can't produce any more thermal energy to support itself against gravitational attraction, and so the thing collapses. And the idea is that it collapses to supernuclear densities, and then the strong force becomes repulsive, and there's a bounce shock, which the core of the neutron star or protoneutron star collapses, drives a shock wave. But that shock wave has to plow through the collapsing mantle of the star, which is made out of heavy elements. So that shock wave has to waste a lot of energy photodisintegrating the heavy nuclei into free neutrons and protons, and also emitting neutrinos copiously. So you're left with the core of this thing, and then this bounce shock, which stalls at a few hundred kilometers. And this happens in all numerical models. So you have a failed explosion in the sense that the shock is no longer moving outwards. The hope is that on longer time scales, hundreds of milliseconds or so, the Kelvin-Helmholtz evolution of the inner protoneutron star emitting its binding energy in neutrinos, that some of those neutrinos interact with this material behind the shock and deposit sufficient thermal energy to revive the shock and explode the star. So that's the conventional or the most popular model for how core collapse supernovae explode. And this is called the delayed explosion mechanism, and many groups throughout the world are working on it. The reality is that most of these things don't work. There are some models that do explode, but what happens when people put in as much physics as they can, often the shock just simply isn't revived sufficiently, or you get a very weak explosion, much weaker than observationally determined. But the important thing to note that even if very low mass stars, let's say 10 or 15 solar masses on the main sequence, can explode by this mechanism, this heating, this explosion mechanism is a competition between the timescales of depositing energy by neutrinos. The neutrino flux is going down over time. And there's also this ram pressure from the imploding mantle, which is also going down over time. And the question is, which wins? And so what you need to know then is what the structure of the star is. And this is a pre-supernova density structure of stars. This is log density as a function of Lagrangian coordinate interior mass. And you'll see that the lower mass stars have very smaller cores and very steep gradients outside of their cores. So they're relatively easy to explode. There's very little ram pressure, and those are the ones that are sometimes being exploded successfully now. But we know there's a whole class of stars which have larger cores and higher entropy cores, let's say 40 solar masses on the main sequence or so. These stars have much larger cores and much shallower density gradients outside of the core. So the ram pressure, there's a huge flux of mass onto the protoneutron star, and it's unlikely that you could push that material out by neutrino energy deposition. And it's thought that these stars form black holes promptly. So there might be a short protoneutron star phase, but then the rest of the star comes in, and you form a black hole of these things. Because that's a very interesting object. So then you're left with a massive star. The surface is just sitting there, but it doesn't know yet that its core has formed a black hole. And the star could just fall radially into the black hole and disappear. That's one possibility. However, it's unlikely because stars are observed to rotate. This is the surface rotation velocity of some stars, and massive stars are, this is breakup velocity. So stars are rotating very rapidly, many of them, and some of them anyway. And so we think that the stellar gas has angular momentum. And furthermore, theoretical models of stellar evolution, these are numerical models by Hager. And what he finds is that the angular momentum in the core of the star has sufficient angular momentum to form an accretion disk around a Kerr black hole or a Schwarzschild black hole. So the gas that's collapsing in the star won't fall radially into the black hole, it'll spiral into a disk. Okay, that's very interesting, because then you have this thing which is called a collapsar. You have a failure of neutrino-powered supernova explosion, and you have and if you have a rotating stellar core. This may not always happen, but these are two relatively infrequent events. But through these together, if that happens, then you get a very rapidly accreting black hole at the center of a massive star, and that forms an accretion disk which accretes at almost 1/10 of a solar mass per second. It's a huge source of energy being thrown into the black hole. And that furthermore, the time scale of the viscous time for this disk is very short. It's milliseconds or so. But as you saw, long gamma ray bursts, or as I said, long gamma ray bursts are 20 or 30 seconds, or even a minute, or even hours long. And so you need a longer time scale in the problem. And that's very naturally produced by the collapse of the stellar mantle that's surrounding the newborn black hole. So the disk is tiny, but it's being fed by the collapse of the stellar core on the dynamical time, more or less, the collapse time scale of the stellar mantle, which is tens of seconds, just very roughly, or an hour, or something like that. There's the accretion time scale. So that's why it's called a collapsar. You form a disk, which is being fed for long time scales, but you have an enormous accretion rate, so you have sufficient energy to explain the luminosity of gamma ray bursts. Furthermore, since the engine is a stellar mass black hole, it naturally fluctuates on short time scales of like milliseconds, as we saw. And so you have this very interesting object. And so I did this in my thesis. It's kind of obvious what's going to happen, right? It's just the gas is going to collapse into a disk. And this is just a 2D Newtonian calculation. They had alpha viscosity, but it had good microphysics. I had photodisintegration of the heavy nuclei, it had neutrino cooling, and so on, and an appropriate equation of state, and self-gravity. And found that the disk formed, and that furthermore, this density at the pole was so low that a small fraction of the accretion energy deposited into this region would produce a relativistic outflow. And I found relativistic jets beam to a few percent of the sky, which is really nice, and then stopped the calculation because it was a non-relativistic code. But so a lot of energy coming out like this. And then also a slower component, this is a wind, which I'll show you later. A slow wind, and that's very interesting because it's an alternative mechanism to explode the star. Forget about the jet for a second. Just the fact that you have a disk that's feeding a black hole, but that can't cool sufficiently rapidly. It's emitting neutrinos, but not quickly enough. That'll drive an outflow. That's outflow. So this is a accretion-powered supernova. So enough energy comes out in this nickel, what we call the nickel wind. Enough energy comes out, but also the nickel to explain the light curve. So type 1 supernova, its optical light comes from the radioactive decay of nickel to cobalt and cobalt to iron. So you have to produce that nickel in order for the star to be visible as a supernova. And so this does it. It both explodes the star and produces the nickel. And it's independent of this relativistic jet, which is responsible for the gamma bursts.
How are you injecting the jet again?
So it's in a cone. So this is.
Are you looking at angle?
Yes, but the angle doesn't matter. There's a recollimation shock that happens further out that recollimates it. So yeah, we varied the angle. Check that it's insensitive. So this is in this model, this is the accretion rate as a function of time. You see almost a tenth of a solar mass per second. But here's the punchline. It's a huge energy source. So tapping a small fraction of that is sufficient for the gamma ray burst energy. There's lots of interesting stuff that actually I think at this point needs to be revisited in more detail. But things like this accretion shock is hot enough to completely photodisintegrate these iron nuclei and silicon later on. In this accretion shock, they photodisintegrate all the way to free neutrons. So this disk is made out of hot neutrons and protons, which are capturing thermal pairs, electron-positron pairs, sometimes creating neutrinos and cooling this flow. So this is a neutrino-cooled accretion flow. There's some interesting accretion dynamics as well. And then what we found is that the spin grew rapidly, so these are rapidly spinning holes, per parameter of 0.9 something. And they created a few solar masses on a time scale of 20 seconds or so. And this shows a movie, which is kind of fun to see, of what this nickel wind does. And you can see it has this episodes of accretion. But this thing is exploding the star, and it's nickel rich. So, and it's also depositing a few times 10 to the 51 ergs, both from the kinetic luminosity of the wind, but also from the recombination of the free nucleons into heavy nuclei, mostly silicon and some carbon and oxygen, and also iron group. And that's important for nuclear synthesis. So this is rare, but it may be an important source of nuclear synthesis. Yes?
Turn off the jet, you still explode the star.
Yes, exactly. This is a kind of a novel way to explode a star that is unrelated to the jet. Jet is presumably being powered by Blanford's NIAD or by neutrino annihilation. Different component. Yeah, so forget about the jet. This is still a supernova mechanism. And what's happening is the disk, the inner disk is falling in, but there's an energy flux through the disk. The gas out here is unbound and blows off the disk and explodes the star.
ABS.
Sorry?
ABS.
What? That's slow. All right, I just want to mention, just because it's worth keeping it in mind, that when these things explode, it's not like the black hole just goes away. It's sitting there, it's accreting for a long time, and these are significant rates. So nothing compared to initially, but they're accreting at, you know, a million of a solar mass per second. That's a lot of energy potentially, and that's going down like 10 to the minus 5/3. So these sources could be persistent for longer timescales, and they may produce transients that can be observed in transient surveys that are being planned now. Let me say also that another way to explode the star is that if you have an accretion disk that has colloidal flux loops in it, and the disk is differentially rotating, it's Keplerian, let's say, then some of that colloidal field is sheared into a toroidal field, and it forms a structure which has toroidal field which tries to expand outwards, but encounters the pressure of the surrounding star. And that forces it, because there's hoop stress in the tower, to be collimated. And what you get then is that some of the accretion energy is actually going into forming a magnetized structure, what's been called a magnetic tower. So we worked out analytically what these would look like to some degree. But what's interesting is that you get a shock in the star, and then you get the shocked star in this cocoon, which I'll show you in a second. But then the core of the jet, what we call the jet here, is almost purely magnetic field. And since there's so much toroidal field, it's hard for baryons in this cocoon to get into the tower, and it could presumably be very relativistic. This is another interesting model, and I'm mentioning it because it could happen with a disk, but it could also happen with a magnetar. So a magnetar is a similar idea. You have a light cylinder, and you have colloidal fields, but outside of the light cylinder, the field is swept back. So again, you have toroidal field that's being injected into this cavity, which gets in pressure balance, and again will form a jet. So in either case, either the disk forms a jet by Blanford-Zayek or by neutrino annihilation or some disk wind, or if you have a magnetar that's embedded in the star and has a light cylinder and also generates toroidal field. Both of these processes will extract energy either from the magnetar or from the black hole and explode the star. So what are the requirements? Is that in order for this process to be successful, you need to eject it to get out of the star before the engine dies. So you need the engine to last longer than the time it takes a jet to escape the surface of a star. And so it has to be 3 seconds or so. So any process that's very short is no-go. It's not going to work. It'll make an explosion, but it won't make a relativistic explosion. You need the jet to get out of the star and continue to be powered at its base before the engine dies. So you need a long engine. And the interesting thing is this engine is much longer than the timescales you'd naturally expect for a stellar mass black hole or a neutron star, magnetar, or whatever. So you need a longer timescale, and like we said, that timescale in the collapsor model comes from the timescale for accretion in the core of a massive star. You also need angular momentum. You can ask me why not too much later if you'd like, but that can be a problem. You need the right range of angular momentum to create a disk around a black hole or neutron star, I guess, to produce an explosion that lasts long enough. And that means that if you had the hydrogen envelope on the star, there's no way these engines are long enough. The light crossing time of a hydrogen envelope is thousands of seconds. So if you had a red giant or red supergiant, you'd form a disk at the center. This mechanism would still work, but it wouldn't be able to get the jet out of the surface of the star before the engine died. So you had a very interesting supernova that was powered by a jet, but you'd never know. If you looked at the star from far away, you'd just see an explosion. You wouldn't know whether it was powered by this or not. So this could be happening more
That
often.
factor of 2 in T-escape is 2 T-light. That varies depending on the...
Yes, absolutely. Yeah, this is just very rough. And Chris has, of course, worked on this also. Okay, just for fun, I'll show you a movie. This is the AMR, Relativistic Hydrodynamics. This is the 5th order code that I mentioned this morning. This is kind of old at this stage, but I think it very nicely shows what happens. There's a bow shock that travels to the star, and then the material can squirt sideways because it's not moving relativistically. So all the material that's in the way that would have prevented this jet from staying relativistic is all pushed into this cocoon of material that also kind of supports the jet in a way. And Chris, this is the recollimation shock that makes the thing.
So what's the lens back to the stuff that's just reaching the head of the jet?
Right here it's 50 in this particular model. We've done 100 also.
Gamma is larger than 1 over theta.
Yes.
That's important.
Yes, it's very important.
It's important for this trapping issue, right?
Yes, absolutely. But here's the important thing. This material is much lower. This is a gamma 1 point something.
Oh, sure.
So that's
Well, it's still in the star, sure.
right. But that's it. See, so the point is it can get out of the way. And then it forms this cocoon, which is this relatively hot stuff. Yeah. Okay. So this issue will come back about gamma. Remind me. Here's a problem, a potential problem. Here's a jet, and here's the wall of the star, the edge of the jet. It can be Kelvin-Helmholtz unstable. As it turns out, so it's something to just be concerned with. A very relativistic flow, it's difficult for Kelvin-Helmholtz to grow. But as you saw, there are these recollimation shocks where the fluid slows down and gets hot and then reaccelerates. So there is a little bit of a danger of mixing too much stuff in from KH. So that's a little bit of a problem, but it might be, whatever, appropriate in the sense that the light curves of GRBs are very messy. So maybe stuff like that does happen. There are instabilities. You have a jet that's forming, sometimes it's shut off by the star. And by the way, it'd be hard to get those time scales if there weren't a star there. So in a sense, maybe the star is a good thing. Okay, so I'm going to move on now and describe, so if there are any questions about the first part, because that's just the engine that's setting up the stage for what I'm going to focus on now, which is what happens then. So you've produced a relativistic jet in the star, and it's gotten out. It doesn't have to be a star, by the way, just any relativistic jet. And then we know that if you deposit energy quickly into a cold medium, there's a self-similar solution. This is completely dictated by its density of the medium and the energy of the explosion. And that's has been solved exactly by Blanford McKee. So for the relativistic case, and by Teller and then von Neumann, the set-off solution, the non-relativistic case. So no matter what the shape of your initial explosion, it'll eventually give you a spherical blast wave, non-relativistic blast wave at late times. What I'm going to talk about is this very interesting dynamics, which is the transition from a jetted relativistic flow to a spherical non-relativistic flow. And the reason that this is a challenging problem is that in this relativistic blast wave, all of the energy is in a very, very thin shell. So the energy goes into a shell that has a thickness that's like the radius over gamma squared. So if you have Lorentz factors of 100 or something, you've got this tiny little, very thin shell of material moving through space, and that's decelerating and spreading sideways, and that's where you observe all the radiation from. It's very challenging, just technically, to simulate this. But that's what we did. So here's the basic idea, is you start off with a Lorentz factor that's much larger than the opening angle of the blast wave. And so initially, you're only seeing this little patch of the flow, because all the radiation is beamed towards you. But as the thing slows down, that beaming angle increases. So you see progressively more of the blast wave. And so the energy is decreasing, but you're seeing more of it. So you get some sort of shallow decline. But then, when the Lorentz factor has declined enough that you start to notice that the jet has an edge, then there's a break in the light curve. So everyone see that? So initially, you're just seeing more and more of the shell, but then it slows down enough that you would have wanted to see more on the edge, but there's nothing there. So the thing just declines even faster. And this so-called jet break in the afterglow radiation of GRBs is how the opening angle of the explosion is determined. So it's very important because it tells you what the true energy of the explosion is. And that's how you infer this. This is the dynamics that we want to do on the computer. So we want to start with this relativistic shock wave, which is the Blanford McKee solution. We want it to slow down as it interacts with the ISM and spread sideways. Okay, so here's a movie just to show you what we do. This is just the initial condition. Hopefully you can see this. So we're just zooming in on our initial patch, and I'm just showing this to make the point that here's this Blanford McKee solution, but really, all of the energy this is a log scale. So all of the energy is this tiny, exquisitely thin shell. And this is what we actually do on the computer. We only do one quadrant. So now we're going to change the scale so you can really see where the energy is. So we're just going to focus in. Nothing's happening dynamically yet. See? So we have this huge box with this tiny little thing. So we use a lot of adaptive mesh refinement to some 18 levels, as many as 18 levels, to resolve this very thin shell. So now we're going to start the simulation. It's a 2 times to the 52 order explosion, opening angle of 0.05. Now it's evolving, and you can see this is where some people thought the explosion would be spherical and not relativistic. No, it stays very relativistic. It's really surprising. For a long time, there's another time scale up here. This is very late. This is in the lab frame. Even much, much later, okay, maybe it's starting to spread a little bit, but still the bulk of its energy is within the initial open angle. Here again is another estimate of what it is.
Sorry, Ron is wrong.
Well, there's a whole host of papers which I think underestimated the lateral spreading. So what we're finding is that the things stay beamed much longer. Yeah.
Overestimated a lot of time about the spread.
They overestimated it, yes, yeah. So we're seeing much less. And it happens much later, and then at very late times, it becomes spherical at very late times. But that takes a very long time. I think just longer than people had expected. And no, I mean, there was the first models that were very good, and they did lots of things well. But they assumed that the jet stayed the top hat, so that when the edge spread a little bit, the whole jet knew about it. And then it just kind of stops exponentially and becomes spherical. That's not what we find. We find that there's a wave that goes in, a rarefaction wave. So late times you get something like this, which people have noted looks like the Fermi bubbles. And it's true, you can argue later. We did this calculation for GRD conditions, but these in some sense are scale-free. So you can kind of scale this also to the galactic center as well. Yes?
When, after the rarefaction wave has reached the center, is there a period of sort of self-similar spreading?
I'm working on that right now. I'd be happy to discuss that with you. That's a very hard problem because you need to do an extremely small angle jet, and it has to be very relativistic. But I am doing that. I'll show you a little, I'll give you a little teaser. That's actually the thing I'm most excited about right now. But no one has seen it yet, is the answer. No one has seen it yet, but hold on. Let's see it's in, I think. So anyway, just to give you a little diagnostics, here's the jet a bunch of different times in the lab frame. And I'll just show you what what things look like on the symmetry axis at the very edge of the initial opening angle of the jet, and also at far angles. So what we get is, it's not so green, but is we get Blanford-McKee, pretty much exactly for the radius, on axis. This is the on axis thing, and these are off axis. So, and then it transitions at late times to set off. For the pi over 4 one, nothing happens at first, but then the shock wraps around, and then it goes boom right onto the set-off solution. So yeah, on axis, you're Blanford-McKee, slow down to set off. Off axis, as the shock wraps around, you go right on to set off.
It's a beautiful parallel between those two times.
Right. You mean this?
No, the intermediate section, the black section above set-off. Is a different parallel to the set-off, so it looks as if something else is happening.
Yeah, there's still, oh yeah, you're absolutely right.
Solid line, you mean, right?
Solid line.
Just mean the solid line.
You mean here?
Yeah, that one seems to have a different power and setup.
Yeah, it does, and it's very bright. The set-off is an attractor, but it's a very slow attractor. I think you'll notice if you have good eyes that it's starting to, but at very, very late time. So it takes a long time for the set-off. Well, this is many years.
Setup shell is thin, so it's hard for one part to know about the other part.
Yeah, but over time, the pressure equilibrium is starting to set in. But you're right, it's still, and I'll show some more of this in a few seconds. Okay, but let's be honest, okay? That looks great. That's just the radius of the shock wave. That's pretty easy to get. It's basically traveling at the speed of light, and then it slows down. What really is kind of a drag here, and if we emphasize a lot, is this. This is the forward velocity, or just think of it as the Lorentz factor. So we were doing a 0.02 jet, and we wanted gamma to be much larger than 1 over theta, so we wanted much larger than 5. So we said, okay, we're going to do 20, and 20 means it's a very thin shell that will put out so much resolution, we'll just use a really big computer, and we'll be able to resolve it. No, we couldn't. So here's what happened, is immediately, just for numerical reasons, it dropped. So we started with 20, for a few hundred time steps it had 20, but then you're trying to resolve this really thin structure. It's this amazingly thin thing, and so the thing spreads out a little bit numerically, and the Lorentz factor goes down numerically. So in fact, we only really got Lorentz factors of about 5, which is exactly the same as 1 over theta. And we're kind of interested in this transition from gamma is much larger than 1 over theta to when it, so see the thing we're looking for, very unfortunately, wasn't properly resolved. So we weren't, even though we tried really hard, we didn't quite get a high enough Lorentz factor. It was only about 5, only about 1 over theta. And other things worked well here. We got the set-off solution at 8 times. We also the energy density, which determines the radiation. Also, we started out at the Blanford-McKee value, but it immediately dropped. that can be important for radiation from very early times in the light curve. So that's with the very early jets. So this is a problem. Even with AMR, we're having trouble just doing these simulations. Okay, so here it is again, but I just wanted to say that even recently, this is just a month ago, DiColi, Bruno, Ramirez-Ruiz have also tried to do this problem, and they see the same thing. So they go down to 10 or something, and only when they crank things up really high in 1D simulation, so this is not feasible in 2D, they still get this thing where the Lorentz factor goes down really far. So the simulations I'd say are still unresolved unless you do a jet that's like 0.3 or something like that. But to do these narrow jets that Chris is asking about, the Lorentz factor would have to be hundreds. So this is the teaser. This is what I've recently been able to do, and I'm extremely proud of. This is the Lorentz factor of 200. This is the Lamper-Nicky solution. So this is very preliminary. I just took it from it. You can see it's a GNU plot from my laptop today. But I think this is going to be a huge deal. So this is, I think, and I don't even know this is the lowest. I probably can go even higher.
Is your adaptive code?
It's an adaptive mesh refinement, but that's not the thing. It was thinking. It wasn't technology. So I'm doing this in a different frame, and when I do it that way, it looks beautiful. So just keep your eyes open.
Why is Lamper-Nicky on it?
It's not always taken at the same spot. So I do the solution at the pressure maximum, and there's a little bit of noise behind it. So just numerical. But if I averaged it out sufficiently, it would go. Okay, so anyway, that's an exciting thing. Because what we want to know is that there was this Rhodes model that said things that, you started out with a 0.05 jet, that it would expand very quickly, like this. So in just a few tens of days, you have the thing expanding out to a spherical explosion. So what we do is we plot from the numerical solution where 95% of the energy is, and we see that it spreads much more slowly. So this is what we see. And so this is the theoretical prediction from Rhodes for a top hat. This is the numerical solution. So the spreading is much, much slower. It takes thousands of days for it to become spherical. And
that difference in behavior must change your interpretation of the spreading.
Yeah, absolutely. Yeah, absolutely. So in particular, I'll show you that, exactly. It completely changes it. So, right. So what we think is the jet brake comes completely from missing flux, not because the jet expanded. Totally different interpretation. Yeah. So here again, another point to make is that this is 95% of energy. This is 50% of energy. That means the blast wave is very inhomogeneous. The edge moves it out a little bit, but a lot of the energy stays focused at the center, which is what you'd expect. I mean, it's really not too surprising. And so this shows that energy per solid angle as a function of angle. So you see, it really is still a jet even at very late times. So you still see. So you still see this. So there's much more energy along the jet axis than near the edges. So it hasn't isotropized. Okay, but anyway, why are we bothering to do all this? I think it's intrinsically very interesting, gas dynamics. But what we ultimately want to do is compare to observations. So what we've done is, and now we're able to calculate light curves. So basically, in the simulation, we save a bunch of time slices of the velocity, density, and energy of all these fluid elements. Then you can just put an observer at some angle, and then just add up all of that emission, assuming a synchrotron emission. So you add up all this beamed emission at a fixed observer time, and then you can create a light curve. This is our goal. And so we've done this here between the radio. We can go to very low frequency radio that's relevant to the COFAR and so on, and then also up to the X-ray. So we have these light curves which come from actual dynamical models, two-dimensional simulations of the blast dynamics. So it's a very simple problem to pose, and this is the result. And we found many things. One is that we do see a jet brake if we're on axis, but we don't if you're off axis. So it's smoothed a lot, and these observers are still seeing the GRB, but would you fit a jet brake here? You probably wouldn't. And then we also calculate orphan afterglows and so on. So calculating the light curves directly from the jet dynamic is important. And so we've done that. We also see a counterjet, and we see different features in the light curves that I think are going to be very important for determining the energetics.
So what exact phase in your calculations does the jet brake correspond to?
What
exact phase of the evolution does the jet brake on-axis jet brake correspond to?
Let's see. It corresponds to the time when gamma is 1 over theta. because it's just missing flux, you're just not seeing the flux. It's not exactly that. Of course, there's some spreading, but it's not very important. Okay, so this is the result. We put these all online so that observers can use them. And I just want to emphasize this point again, that this is on axis. This is the most likely observer, 2/3 of theta jet, and this is the edge thing. So here's a beamed flow that does have a jet break, if you were on axis, but no observer is on axis. No one, almost no one. Most people are out here. Out here, I don't know. There's a little bit of a turnover, but probably a single power law is preferred for this guy, even though it is a jet explosion. It's just that you're seeing it off axis. So this is important because Swift wasn't detecting jet breaks and still doesn't. So here what we did is we created synthetic Swift data from the simulation. And this is what it would look like. So we put in instrumental noise and so on. But look at this. If you're on edge, you would just, this single power law is definitely preferred. So here, on axis, you might prefer a broken power law with a jet break around here. But here, you don't. So the fact that you don't see a jet break in the Swift data doesn't mean that the jets are very broad. It just then means you still can be seeing narrow jets, but you're just seeing them from the edge, from near the edge. So it's very simple, and we put in a new formula here where you just have to, basically what's happening is, if you're on the edge like this, the jet looks like it's wider. It's just obvious. It's only here where you see the jet break over here. Okay, so that's nice. The other thing that is very interesting recently, I hope I can rerun that, is just to show, it's going to happen quickly, just watch it and then I'll explain what happened. Okay, so this is scale invariance. This jet has 100 times less energy than this jet. And unfortunately this isn't clear, but there's scaling parameters, kappa and lambda, where if we just rescale the jet simulation at low energy, it is exactly the same as the larger energy. We can do the same thing for density. These things are completely determined by energy, density, and initial opening angle. So the point is, if we do a single simulation for a given initial opening angle, then we can scale that to any circumference density and any energy. And so we can write a code that automatically generates the dynamics from just a single simulation and use that to iterate over that observed data. So that's very powerful. And so we did that. And so this is an example. Here are the data, and here is our best fit. And so we find some differences with previous models, which I can tell you about later. But these curves were done by iterating over many different explosion energies and densities until we were able to get this best fit model. And then we published the best energy and so on. Okay.
How would you approach this in the case where you have different light curves and different wavelengths?
That'll be the most difficult thing. So we have to choose initially the ones that are originally pretty nice.
Sure.
But as you start to see that, then we'll have to tackle more. Then we'll have to do simulation. So I'm saying is for the simplest cases, all the information comes from a few simulations.
In some cases, in the optical, you see this beautiful declining power law from the prompt versus, and then you have this sort of plateau like you do during the X-rays.
Right, yeah.
So it's not a one-component thing. Right?
Absolutely, yes. And that's exactly the point, is that we're trying to say, this problem is extremely simple. Let's just kind of do it that. And then all the complexity, all the interesting ones are left over. Yes, exactly. It's an exception, but at least if we can understand this dynamics, we can kind of remove that out and then find out what's going on for the more complicated ones. Okay, now interestingly, this really surprised me. First of all, no one seemed to really appreciate this fact, at least as far as I can tell, that these things scale. It's a complicated flow, but so you can scale these things out.
The opening angle is not. There's the other two parameters.
Yeah, you have to do a different simulation for every opening angle, and that's what we did. We did 20 opening angles. Yeah, that's exactly right. But check, this is even more surprising. You do all this simulation, all of this, and then you calculate the radiation from all these fluid elements and so on. That also scales. So you can do this on the level of the light curves themselves. Here's the light curve for EISO of 10 to the 50 ergs. And then if you wanted to do the same light curve, all you have to do is scale the thing by this kappa parameter of 0.01, and you get the light curve exactly for this less energetic explosion.
For a given opening.
For a given opening angle. So everything I'm saying, yeah, so the opening angle matters, but the point is that we only need to do one simulation for each initial opening angle. Then we can do all of the iterations, and this is trivial to do. So we're writing a code now that takes the dynamics from these simulations, and then you can just fit. So you have some data, you can just keep on fitting it. You can vary the energy and the density as much as you want, and it automatically will count through all of it and find the best fit.
You could also vary the density of power law.
Yes, you can have a power law density. You just can't have any characteristic scale, length scale.
But it would be a different simulation.
Yeah, but we'll do that. We'll do, so these are constant density, but we'll obviously also do different power laws for density. Yeah, and add that to it. Okay, and then why do we want to use these? It's because there's all these broadband surveys, the all-sky surveys, transient surveys, time domain astronomy is coming, or it's already here. So we want to, so for example, these are low energy gamma ray bursts at a very low frequency, and so these would be light curves for short bursts that are off axis. So when you look at the sky, there'll be, some short emerging neutron stars, or for whatever, that may have been gamma ray bursts for some people, but if you're off axis, you'll miss them. And so this is our prediction for what the light curves would be like if you were off axis. So most observers are in the equator, so most observers will see this. And this is, so for this very low frequency. Oh, also we do the radiation transport, including synchrotron self-absorption. So we can calculate very low frequency things. And then we can do things like rule out supernovae. These are radio supernovae. And if they were GRBs, we say they would have made bright afterglows, so they ruled out many of them. And that's consistent with what sort of it all found. Okay, sorry about this. Ignore that. This is the website, Afterglow Library, where we're putting everything. So you can just go there and you can, actually, hopefully I can show you. That would be ideal. Actually, maybe if I click on it. Yes, I'm not sure I'm on the internet. Oh, it's too bad. Yeah. Well, if you want, come ask me and I'll show you. Or just go to this website when you have time. And you can see all of the light curves there. And you can click for different energies and opening angles and observer frequency and so on. And you can download the light curves. So I think I've said all this. Just to summarize that this very interesting dynamics. But what I'd like to move on to now is something I was discussing, and I'll do this semi-quickly, but I think I can still get the major points across. We did some particle and cell simulations to look at shock acceleration. This is pretty straightforward. You get kind of instabilities in this collisionless plasma, and you find that magnetic field is generated, and that particles are accelerated from gamma 2 to gamma 20, and so on. And this is so particle and cell simulations can do this, and Spitkovsky was the first to do this in detail a few years ago. We've also done it. But what we find is, very importantly, is that the magnetic field is generated. It does have an epsilon d of about 0.1, but that's just on a few skin depths. That's an extremely thin thing. It's not relevant. Well, but yeah, okay, I agree. It's a very, very thin thing. So this is to motivate. So everyone sees that you can, of course, you've got two streaming plasmas. There's some instabilities. You can generate magnetic field, but on an extremely thin thing. Okay? But people do mention sometimes that this is the source of magnetic field in afterglow jets from gamma ray bursts. I think it's unlikely. So what we've done, I don't have this movie here, but if you go downstream, instead of following the shock, if you go downstream, you see that this magnetic field goes away very quickly. So it doesn't fill the volume, is the point. So what we've been looking at instead is relativistic MHD, and it's relevant for all these things. So I'm interested in GRB afterglows, but it's also, of course, relevant for AGN, SGRs, microquasars, supernovae, and these mergers, very interesting for gravitational wave sources, also the early universe. And when you have Lorentz factors at this scale and internal energies that are relativistic as well, so relativistically hot gas. And these equations are simple to solve. I don't even know why I put them here. The point is that we solve these equations in flux conservation form, but the only point here is that the pressure enters. So when we're looking at relativistically hot gas, vortical structures are affected by the pressure wave. So there's a coupling between vortical and acoustic modes that's novel, and it's purely relativistic. So what we do, and this is actually a fairly old simulation.
And there was a vortical mode?
Oh, just a curl-like.
Sure, okay.
Yeah, but there's something called the generation of acoustic waves by convection.
Yeah.
Which is very much along those.
But no, exactly. My only point is that, of course, that happens, but in the relativistic case, there's a coupling that doesn't exist. That's my only point. So that motivates me to look at, and this is work we published this year, or actually last year, I guess, a pretty high resolution, and this is magnetic field you're looking at. So what we do is we just stir the box, and we start with a very weak seed field. And you know in reality there's always something to drive. So the shock is traveling over something that's clumpy, and you generate turbulence. And what we find is the turbulence always saturates at a few percent of the total energy. That's an epsilon B of 0.01 or 0.05 or something. That's a lot of magnetic energy. So energy is coming out of the flow, going into turbulence, and it's winding up magnetic field. So we've also looked at this in the supersonic case. So this is supersonic relativistic emission turbulence. And what happens is, in this case, we're looking to see how long-lived it would be. Because some people had suggested that relativistic eddies are what cause variability in shear B's. But we found that it decays very quickly. It's not too surprising because it's supersonic. But we found lots of interesting things. One of them is that if you start with a weak initial magnetic field, and we do higher and higher resolution, so this is 128, 256, 512, and 1024, we converge at a magnetic field of a few percent. We can also find that the magnetic energy is almost in equal-partition to kinetic energy, calculate the Alfvénic Mach number, and so on. But anyway, this is what it looks like. You get these structures. This is at 1024.
Sorry, you said two things. One is that magnetic energy is a few percent, and the other one was that it was in equal-partition. What's
with the kinetic energy? It's a few percent of the total energy. Most of the energy is internal here. So we're thinking of a strong shock that's dissipated. Now it's relativistically hot, so most of its energy is thermal. But it's also got kinetic energy. And that is
was there anything holding it to a few percent with the internal energy?
Yeah, well, what I think, although I'm not totally sure about this, and I'd like to discuss it with you guys, is that there's a turbulent cascade, and that's 2% is the total energy of the box. You've got modes on all scales. When it's 2% total in the box, the smallest scales have wound up to super equal-partition and they spring back. So I think it's just the turbulent spectrum that means that that's the highest field you can support. That's what I think. But I'd like to discuss that more eventually. Do you understand? So it's just that at very small scales, the field is so crinkled that it can't.
What range of scales can you resolve?
We resolve scales of about 8 zones. It's about 100. So yeah, I'll show you.
Is this really a shock or you're just stirring the box?
Just stir it.
Yeah.
Yeah. So this is different. So the idea is that there is a shock out ahead, but that generated some turbulence, and now we're just studying the turbulence by driving the box at a larger scale. And this is what the magnetic field looks like. It's actually pretty well resolved, and that's the point. These red islands are high magnetic field, the blue ones are low. So even though the overall magnetic field is a few percent, let's say 2%, there are regions that are sub-equal-partition and super-equal-partition.
So you're saying, though, that the second partition, the magnetic field is in partition of kinetic with turbulent motions?
Yes. Yeah. Yeah. Oh, okay. Now here's another interesting thing. So this is very new. This is we're about to submit, but we're doing this for neutron star merger conditions, and I mentioned this to some people at lunch already. And what we're finding is that the maximum field that we can get is actually very large. So for low effective resolutions, we don't converge, but we run a series all the way up to 1024, which isn't done yet, unfortunately. But you can see the 512 one. It rises very quickly and then saturates. So we think this is converged.
So how are you setting this up?
Okay, so it's the same thing. We take a box.
3D?
3D. Yeah, 3D. Yeah. Yeah, it has to be 3D. And then we drive that on a range of wave numbers at low K. And then we just start with a very weak initial field, periodic boundary conditions. This has an HLL Riemann solver, which is very accurate. And then it's unsplit to a Knopf code. It's a very nice code.
And this is relativistic.
Relativistic, yeah. Relativistic MXV. And what we see is that we have maximum fields of a few times 10 to the 17. A huge magnetic field.
This is the peak field, or is this
This is the peak field. Sorry about this. Okay, I'll show you this. These guys who did global simulations, very impressive. I'm not criticizing them at all, but they were claiming that the magnetic fields were always the same. You always grow by maybe an order of magnitude. That they started with the weak field, it saturated 10 to the 9, 10 to the 11, 10 to the 13. So they weren't seeing much growth.
Are you getting large scale fields in this?
No, this is all. I mean,
No.
yeah, I can show you I have the power spectrum.
Large scale fields are crucial.
Yes, yeah. So I'll show you the power spectrum of the magnetic energy. But anyway, so here we do the same thing. We kind of get the same result. But it turns out that it's just a very early time evolution. If you wait long enough, they do saturate. So So this idea that they only go from 10 to 10 to 10 to 11 or whatever is just this very early time. You have to let it, the turbulence saturate. And when it does, you get this value. This is something I'll talk about later.
So when you talk about this peak, is it in a single cell? Is that it, or you?
It's just the max over the grid.
Yeah, exactly. So let's go back to Chris's question. If you average over the whole thing, right?
Oh, I have that plot. That's what I was just looking for. If you don't mind, let me just, I have it in a different, I meant to copy it over. I told people this might happen earlier today, so I hope that's okay. Let's see. I'll find it in a second. And then I'll stop.
Should you tell us what tests?
Yeah, okay, we'll tell you about tests. But first, let me just show you this result. So this is the magnetic field that you just saw. This is that. This is B max. This is B mean. Okay, here we go. So B mean is actually 3 times 10 to the 16. Yeah, and that's starting from, so we started out with 10 to the 14, then 10 to the 12, then 10 to the 10. So even very weak fields, this is a tiny field for a neutron star. Look at that. It grows by almost 7 orders of magnitude.
What's the eddy turnover time in motion?
Eddy turnover time, of course, depends on the scale, but on the small scales, it's many, many. We should put this on eddy turnover
That's
time.
100 AOV times 4, 10 to the 9 counts.
It looks like more than that.
So interesting.
Yeah. This is very new, by the way, and so it's not published.
And this specific to relativistic.
No, I think it's not specific to relativistic. We wanted to do it relativistic because that's
The emotions here are not going to be relativistic.
No, but it's relativistically high. Not very, but it's a little bit relativistically high.
Well, in the merger, the stuff that merges is not relativistically high.
It's a little bit.
And the temperature is relativistic for the
It's like
positrons,
right.
but for the nucleons, it's sub-relativistic.
It's not relativistic. It's true. This probably would be the same relativistic. But nonetheless, these are the real equations. So, yeah.
The same thing.
Yeah. Yes, you would. I think you would. Sorry, go ahead. The order, it's what I was saying before, is that it gets into equipartition with the kinetic energy.
It's just the rho v squared of the end.
Yeah.
Oh.
They can't handle it.
For the mean field.
No rotation.
No rotation. This is a box.
That's because of the
It's
size.
just a box, so it's like a local patch.
The mean is
I should wrap up, it looks like. Let me quickly talk about tests. There might be something to show you here, but I think I'm going to move on from this stuff. Okay, actually, how do I do this? This is...
You have time, don't worry about it.
Okay, well, let's stress out. So I think we were seeing tests in the other one.
Yeah.
Okay, so TESS is a code, a new code based on a dynamic tessellation of space. And what I'll show you is a movie that I showed, and here's an example of it. And the idea is, I don't know if you can see this, but the cells are no longer square. They're now generated by the Voronoi tessellation, which means that any point in this cell is closer to a point right here than any other of these mesh generating points. And what happens is the mesh adapts. And the best way to see it, I think, is to show you the movie that some of you saw this morning, which is of the Kelvin-Helmholtz instability. And here it is. And what it shows is a shear layer. And what I'm going to do is zoom in. And so initially the grid is rectilinear like this, but then you'll see what happens. What happens is the grid distorts. See, it's forming these cells, and the cells kind of rotate. And what that does is it maintains this contact discontinuity between the two fluids to excellent precision. So you can see, even at, and this is a very low resolution simulation. So you can see here that there's one zone at most in this contact discontinuity. And so this code, we think, is very good for solving some of these problems. One of the problems, which I mentioned this morning, is that relativistic shear flows are difficult to solve because of diffusion across contact discontinuities. So this code can do that kind of thing really well. And so, and let's see. And also, more recently, we've adopted a version of this code in something that we call Disco, which is a similar code, but it uses a mesh that's cylindrical. And this shows what happens when you have a passive scalar. So it's not diffusing material, which other codes do. So a code that's fixed mesh diffuses like this. So let me go back and explain very quickly. Normally, with an Eulerian code, you have a mesh that's fixed in space, and the fluid is advected across the mesh. And there's an error associated with advection, and that's what all these yellow regions are. It's an artificial mixing due to a diffusive code. The Disco code doesn't do that. So you can see that the mesh is actually moving with the fluid. We're actually moving the faces of the fluid with the contact discontinuity between these two cells. So this is, by the way, we do these tests at extremely low resolution on purpose to show, I mean, of course we can do much higher resolution. That doesn't tell you much because everything eventually converges. So we're showing you purposely low resolution to show that even at ridiculously low resolution, it still maintains these structures. So I think this is going to be very important for things like MRI, where you really want to resolve structures.
So Supernova here, you're basically trying to take out the main sort of annoying dynamics, but not doing all the way this folding along like you're doing in tests. So this is numerically simpler, I guess. Or
yeah, it's also, when you have a constrained grid, it's easier to do things. There's less noise. In the tests, the zones faces sometimes rotate quickly to get a new Breuer tessellation. That introduces some diffusion.
Right.
So if we don't, in the case where you have a disk and we kind of understand what the dynamics is already, we may as well use this, because the main advantage is to have the faces moving at the speed of the fluid, so you remove that error, and you're solving all the dynamics kind of in this co-moving frame. And let me just show you one application of this, and then I'll quit. The application, hopefully is here, is to protoplanets. And that may seem very different, but it's very relevant, where you have a disk like this, like you're seeing, but it's embedded, inside of it is embedded a protoplanet, so a very low mass planet. And so recently, Dong, Rafikoff, and Stone have done these shearing box simulations. So you take this little protoplanet and you put it in a shearing box, and presumably there's a disk here, but they solve it in this shearing box around the protoplanet, and they do high resolution, so they're able to see, like if it's a very massive planet, this thing will open up a gap right away, and this thing will be a shock right here. But for a low mass planet, it's a much more subtle. It's a linear wave that they've resolved very nicely. So it starts out as this kind of smooth wave, which gradually steepens into a shock far away from the planet. But this dynamics is very important for calculating the migration of this protoplanet through the protoplanetary disk. And these are very nice simulations. But they're not global, because what we want to know is really how does the disk respond to the protoplanet. So what we've been able to do with this code, our first use of this code, is to do a protoplanetary disk. And here's what we get. These lines are from the PowerPoint. So here's the point, is that, so they do the shearing box. We do it in this kind of global simulation. And this is at extremely high resolution, and the grid is moving with the planet. And so here's the thing. We match, here's the analytic prediction for the position of the shock. So we match that almost exactly. So this is, And then here is the thing I hope you can see. Isn't that nice? So this is the same thing, but in a global simulation. So we're also able to get this linear wave that gradually steepens. And this is interior of the planet, and this is exterior of the planet. So we'll be able to calculate, and we're doing this right now, the torque density of the disk due to the dissipation of this wave as it propagates into the disk. And that'll affect the accretion rate of the disk, will also affect the migration rate of the protoplanet.
Is this planet on a wire, or is it live?
This planet's on a wire, but we've implemented also the Kepler, so we can also move it. But the first thing is we just want to see what the, So, okay, so I'll stop with that. Thanks for your attention.
One or two quick questions.
So
So the stuff with the mesh, moving mesh stuff, I mean, is that not finite element? Isn't there?
Well, I mean, you can think of it like, I kind of consider it to be finite volume, because what it is we're solving equations for fluxes through surfaces that are finite volume. Normally the finite volumes are cubes, in Eulerian cubes, or logically cubes. So the difference in the moving mesh, in the Voronoi code, is that those faces are changing and the shape of the cell can change over time. Finite element is usually used in engineering when you use some sort of pseudospectral or Galerkin method. I don't quite know what the technical definition between finite element and finite volume, but I consider this to be a finite volume code because it's very similar to Godunov code, so it can handle shocks really well because it solves Riemann problems at every face. So it does that really nicely. But in addition now, the Godunov code have problems with contact discontinuities. A shock always wants to steepen because the sound speed's faster here. So a shock, even if you're numerically diffusing it, will still steepen. A contact discontinuity won't. There's no, so if you have two different fluids and there's a discontinuity between them, there's nothing to keep that discontinuity sharp. So as that discontinuity affects across the grid, it just diffuses numerically. And that's a major problem with Godunov codes. This solves that because the faces are moving with the contact wave, so there's no effective flux, there's no effective error. It's minimized, so it's relatively small. So that's the main advantage.
Is this particularly suitable for shocks? For example, if I have weak resonance of locations where the fluid experiences stronger pulse on the planets, would that also have defined the resolution automatically?
Yeah, it doesn't. So it does that kind of thing extremely well.
There's no shock, right?
There's no shock, exactly. So that's the whole point of this plot, is that it does start out as a weak perturbation. This is not the case with a more massive planet where you just form a shock. This code would do extremely well at. But what's new here is that it also does well for these weak, very subtle things that are hard to do. That I believe, in my opinion, the fixed mesh codes and also other codes have been very diffusive with, and we would not have been able to resolve these things in a global simulation. That's in fact why they went to the shearing box in order to get enough resolution just close to the planet so they could see these very subtle waves. So the real step forward here is that we're able to do that in a global simulation. So yes, it does do these very weak things very well, but it also does shocks very well. It's a good enough field.
We'll break for cookies. If you have more questions for Andrew, we'll also be taking him out for dinner tonight. So if you want to join us, send me an email and let me know if you're coming. And let's thank him again.